Hello everyone and welcome to this advanced tutorial. It is prepared to explain how U-Mesh Motion subroutine is used for 3D cases. In this workshop, we are going to simulate tire tread wear using the U-Mesh Motion subroutine. The tire shape looks like the picture on the right side of the screen. This tire moves on a rigid surface. If you zoom in on this part of the tire, you will notice that the tread part of the tire is separated from the simple part. The speed of this tire is equal to 32 km per hour and the distance it travels is equal to 32,000 km. We want to obtain tire wear at this speed and distance using the Archard wear model. The method of creating the primary model. As mentioned, we first model this primary part that constrained axisymmetric and we call it axisymmetric model. That is, the model revolves around a vertical axis that exists here. The model looks like the picture on the left after revolving. In this picture, as you can see, only half of the tire is created, and the other half will be reflected relative to the center plate. It should be noted that the modeling of the workshop is not done in the part module in the graphical interface of Abaqus or GUI. And this is done by input file writing, so this makes it more appropriate to mesh in wearing regions. Further details on the modeling steps will be provided in the writing of input file section. Because there is wear, the size of the mesh is significant in places of wear. So the Archard model is used for wear, the formula of which is given here. Q dot is the amount of material that would be lost due to wear and tear, and is called volumetric material loss. K is the dimensionless wear coefficient called non-dimensional wear coefficient. H is material hardness. P is interface normal pressure. A is interface and gamma dot is interface slip rate. K and H are constants and we need to provide them as inputs to the subroutine. If we write this relation based on time, it will be as follows. In this regard, P and gamma dot are a function of time and displacement, so integration is performed on them. Because our problem is a steady state and the tire speed doesn't change over time, the problem is time independent. And hence, all time-dependent parameters are removed. Also, since dA is equal to the tire area that is in contact with the surface, it can be written as multiplication of the width of the tread by displacement increment. As a result, this relationship can be written in the form of relationship number 4, which is called local material recession rate. Since the width of the tread is constant, we can conclude equation 6 and write it as sigma. Note that Ti is equal to T and Ai can be equal to T multiplied delta Si. Thus, integral equation will be changed to a sigma equation and Q dot is equal to this sigma in equation 6. As a result, the H dot can be obtained from equation 7 and by placing equation 5 in this equation, equation 8 can be obtained. Note that in the U-Mesh Motion subroutine, we have to return the wear rate, or H dot. So let's go to the next point. We use the star restart command inside the subroutine. Restart allows us to save a certain number of results and use them in subsequent analysis. This is done by this line of a specified code, and FREQ equals 100 means in each 100 increments the results will be saved. Revolve the axisymmetric model with the codes specified in the red box. If we zoom in on the tire, we see that each node on the thread has two positions. Consider this spotlighted zone. The L streamline specifies the number of the horizontal line on which the node is located. For example, red is the first point and yellow is the second point, and it continues until 27 nodes, because we have 27 nodes on the thread. L position, which specifies on which of these colored lines the node is laid. In the subroutine, it is essential to specify the distance between each node and its closest nodes. For example, here we specify the distance between node next and pre with L2 and L1 respectively. We also need to specify the segment length of this node. To do so, conventionally we consider the mean of L1 and 2 equal to the segment length. The element types used in this analysis are presented in this table. CGAX4 is a stress displacement element which twists and it is in quad shape. It is actually for the axisymmetric model. Its active degrees of freedom are 1, 2, and 5, which 5 is for twist degree of freedom. CGAX3 is the same as the previous one, except it is in a triangle shape. SFMGA is denoted to surface elements and it is 2-node linear with twist. If we are in the non-zero position, we need to calculate the number of worn nodes inside the subroutine, which are the master nodes. It means master nodes are on the depth of thread. In order to have the image of this node in the direction of x, y, and z, we have to calculate theta here and get the cosine of the angle of wear with each of the directions x, y, and z, so that we can have the image of wear on the global directions. The inputs we need to define for subroutine are listed here. N streamlines is the number of nodes that existed on the one of the vertical lines of the completed model. NGN-LM equal to 48 is the number of nodes on the inner of the tire, which is equal to the number of streamlines. NRV offset is the value that will be added to the revolved node's identity number. NREF offset is the value that will be added to the reflected node's number.